at section 15.1. 15.1 is a topic that seems to not confuse people, but when you're a kid, you always ask the question why when you see somebody like in like the pool. Ever look at somebody in a pool and it looks like their head is shifted over by like a foot? Ever seen that before? Let me show you what I mean. Let me bring up an image. What? No, not of me in a pool. Is that what you said?
What? Do you have any beach photos?
I want to show you an image of what I'm saying. Hold on.
Were you a lifeguard in a past life?
Was I a lifeguard in a past life? No.
I'm pretty sure you were on Baywatch.
So take a look at this image for a sec. So this is a famous picture of an Olympic swimmer. And she was swimming and take a look at her head. It looks like it's literally been decapitated, right?
Are you sure that sounds just like abstract art?
No, this is actually an image, man. It's not a joke. The idea behind it, though, is that the light rays that travel between different media, like air to water or air to glass, get bent as a result of change in velocity. That's what's happening. So refraction is simply just that. The idea that when light travels through different media, so from air to water to glass, or air to water, or air through glass, it's going to bend because the velocity of the light changes. That's the real reason. Okay, so that's the idea of what we're going to look at today. That was just a quick image. The three main objectives are going to be to recognize when refraction actually occurs, identify the direction that the light will actually bend in, and then use Snell's law to determine the angle itself. Okay, so we're going to try and figure out what that angle is that it reflects or refracts to. Look to begin at an example of what refraction looks like as far as looking at two media. So first, refraction is the bending of a wave as it passes at an angle from one medium to another. From one medium to another. If waves were straight on with the media, it would go straight through. If it came down at 90 degrees or if it was parallel to this normal that you see here. So if the light wave happened to be traveling straight down, it's going to continue straight down. It's when it occurs at an angle that the other part gets bent. Just by inspection, just by looking at the board or looking at your iPad here. For this first scenario, air to glass, which angle is bigger, theta I or theta R? Theta I, right? Theta I, take a look at theta I. If we pick the number for theta I, I'd maybe say it's around 45 degrees. What would you say this angle is here? 40, okay, so around 45 degrees. And then for the bottom one, what would you say that would be? 10 or 15 degrees, okay? So it's clear just from looking at the picture, but let's discuss what's happening here. Okay, let's discuss what's happening. So, when light moves through air, it's moving very fast. It's moving at the speed of light. Now, if it's not a vacuum, it's really a little bit less than the speed of light, but we're going to assume that it's the speed of light, okay, for air. But when it hits glass, what happens is it slows down. The speed of the light wave actually slows down. And the wave fronts start to back up. And that backing up of wave fronts causes this to bend toward the normal. See this dashed line here? The vertical dashed line? You can jot down if you want to write that's the normal, if you remember. Normal is always perpendicular to a surface. So the normal, or the vertical, is the dashed line. And when light slows down, when it goes from a medium of air to glass, it bends toward the normal. Thus, theta gets reduced. So the theta I, the incident angle that you got, is then reduced to give you theta R, the refracted angle. When you're going from fast moving media to a slower moving media. So again, here, air is fast, glass is slow. And think about that logically. Here's a light wave traveling, right? Not much intersecting in air. And then suddenly it's glass. Aren't there a bunch of molecules there? Aren't there a bunch of boundaries, atoms that this light wave is going to intersect with in the glass? The glass physically slows down the light wave. When something gets slows down, the wave fronts get all backed up. So suddenly it's like this, but now they're all slowing down. So they're all moving back a little bit. And that causes this angle of refraction. So we can jot down a generalization if we'd like to. When moving from a fast or faster moving medium to a slower moving medium, the light wave bends toward the normal. When going from a faster moving medium to a slower moving medium, the wave bends toward the normal. Okay, that's why you go from 45 to 15. And the second part, what could you say? Somebody extrapolate what we just said, yeah?
When you go from a slow medium to a faster medium, it bends away from the normal.
Yeah, and you can clearly see that in this one, right? So going from glass to air, we're going to see that theta I is quite small and theta R is quite large. So the medium or the light wave bends away from the normal. So maybe now it's 15 originally, and then this is 45 down here. Okay, so vice versa, as we're saying there. Vice versa. Again, the reason is because of the speed of the light wave itself that is changing as a result of going through a new medium. Okay, going through a new medium. Any questions on that so far? This is going to be the basis of today's lesson, this idea. So this needs to be clear and understood before we can move on to the next part.
And is there like a direct proportion between the entry angle and the resultant?
That's what we're going to come up with right now. We're going to discuss how you can figure out the proportionality of those two. And it's going to be a material property, James. Remember how mu for like wood and concrete would be a pretty high mu value. But mu between a hockey puck and ice is a low mu value. It's an inherent property. Or the density of one object is greater than the density of another. We're going to look at a property in a moment called the index of refraction, which allows us to figure out that proportional or that change in theta. Okay, it's not necessarily going to be linear, but you'll see what it is in a moment.
I don't understand how big a glass medium.
So imagine light is traveling from outside and it hits that glass right there. Okay? Hits the pane of glass. While inside the pane of glass, it's going to go at this angle right here.
Just a small thing?
Just during that little thickness of glass, it's going to alter its angle. But then when it comes back out of the glass into air, the angle is going to come back. So what you're going to end up getting here, and this is a question that's really interesting because we're going to notice that, anybody see my stylus? We're going to notice that if we go from air to glass back to air, there's no effect really. Only when it's in the glass is the change. So let me draw what I mean. So write air here, glass, and then air. So a light wave comes in at a very high angle, say like, from the normal, say like 50 degrees or so. It gets bent dramatically so that it's much closer to the normal now. But then when it comes out back into air, it gets bent even further to a new normal. So here's the new normal now, right? The area or the location of intersection. So there are an infinite amount of normals, right? A normal just means a vertical line. So it started at this normal here, it got bent, but then it's going to get bent back, like this one was bent back when it went from glass to air. So the result is that when it gets bent back like this. And this wave end up being parallel waves, and you can see that if you extend them. Okay? But while in the glass, it gets bent. Okay? That makes sense? So there is a small amount of bending there, and then it's going to change. Now, this is not as useful as maybe when looking at a body of water, because you're going from air to a lot of water, where it's not coming back out of the water. So that bend, or that morphing, or that change, or that vision you're going to see that's different, is going to appear a lot more emphasized when you're in like a big body of water, as opposed to a pane of glass that you don't notice it, obviously. There's nothing in the glass. You can't see the bending. But if you see a person in water, you're going to see the bending of the light in the contorting of the body.
So if you do like a person's body and then you put, I don't know like how you do it, but
Yeah, if you could encase them in glass, you're saying?
no, like only like from like say like the torso to their knees and then they're at the bottom of their legs or in the air.
It would be like that middle piece would be shifted over. Yep. You'd be like cutting somebody. You ever see when the magician puts the person in the box and then saws them in half and opens up the box? Or they like saw them in spots and move, and they'd be like sawing somebody's body in those spots, sliding that over, and the other parts would remain where they are. That's what it would look like. Yep. That'd be kind of interesting to see. I don't know how you would do that though. I guess if you stood behind a body of water in some sort of case, but you have to be in the water, I think, for it to.
Well, what if you had like rubber like
Yeah, gaskets.
real
Yeah.
life?
If you had gaskets around like your thighs and around this part, sure, it would work. That'd be kind of difficult to do, or when would you ever do that?
Weird, though.
Yeah, it would be weird. All right, let's go on to the next thing. So what we're going to do is we're going to define this thing called an index of refraction. This is going to allow us to mathematically figure out the angles of which we are seeing refraction in these problems. Now, what we're going to notice here is that we have n equals the speed of light in a vacuum to the speed of light in a given medium. What is the speed of light? Who knows? Who remembers, Luke?
3 times 10 to the 8.
Yeah, 3 times 10 to the 8th. So the numerator is going to be 3 times 10 to the 8th. And what did we say about the speed of light? It is a what number?
Infinite? Yeah, infinite? No, it's defined.
Finite. It is a limited number. It's a maximum allowable velocity of any particle in the universe. So everything is going to travel either at the speed of light or less than that. Agreed? Now, what did I say a moment ago? When you go from light to another medium, it what? What happens to the wave fronts? They all...
Change speed.
Yeah, they change speed. So going from air, where you're traveling at the speed of light, and then you're hitting glass, where you have to suddenly hit all the glass particles, it goes from a high velocity to a lower velocity. So what we'll notice is that in this equation here, c is in the numerator. What conjecture can you make about this fraction's value always? Because c is in the numerator. What could you always say about this fraction?
It's going to be greater than 1.
Greater than or equal to 1.
Yeah.
Yeah. If you think about it, can anything be bigger than c as far as velocity goes? Anything? No. C is the maximum allowable velocity, the speed of light. So v has to be something less than that. So if you have a big number, like 7, and anything smaller than that, anything smaller than the numerator, is going to make the fraction greater than 1. 7 over 2 is 3.5. 7 over 3, 7 over 4, 7 over 4. Anything where you have a larger number over a smaller number is going to have to be greater than 1. So the index of refraction must be greater than or equal to 1. Greater than or equal to 1, no matter what. Now, in air, what would you say the index of refraction is? What is it?
1.
Yeah, just 1. Because we said again, we're assuming the speed of light in air is the speed of light c, even though it's really in a vacuum, but it's so negligible that you could say it's really just c over c in a sense. So in air, the index of refraction is 1. Every other material has an index of refraction bigger than 1. James?
So if velocity of a wave is frequency times wavelength, which is altered by that movement medium? Or is that how it works at all?
No, you're definitely right. Let me think for a sec. Is the frequency or the wavelength altered? Okay, so it depends on the wave, but like a wave that would propagate in 3 dimensions like light would have wave fronts. All the wave fronts get backed up, so the wavelength would be reduced. The wavelength would be reduced.
Are there going to be like a lot of problems where you say like, find the n in the air and then find the n in the water?
No, all the n values are usually going to be given to you. They're going to be given to you, and you're going to calculate the angle of which refraction occurs. Or I'll give you the angles and stuff. I'll go over them in a minute. We didn't get there yet. I'll give you the angles and stuff, and you're going to have to find the value of n. Now, if you were told that the speed of light in, I don't know, water is x meters per second, you could put that speed here in the denominator. You could put 3 times 10 to the 8th in the numerator and divide them and get the n value for water. So you could always determine these just by dividing 3 times 10 to the 8 over whatever the speed of light is in that medium. Okay, you could always determine it, but that's pretty trivial. So this formula is more of a relationship that we're going to use to understand what n really is. Okay, this is not going to be used very much mathematically, more of conceptually, so we understand that n is a ratio of the speed of light to whatever the speed is in a given medium. Okay? Alright, so let's take a look now at a table of n's, just to get an idea. Okay, just to get an idea. So as you're going to see here, take a look at air at the bottom right first, please. And this is what I meant when I said it's pretty much negligible. Look at the N value of air, what it really is. So it's 1.000293. So we say that the value of N in air is just 1. Okay, it's just 1. Even carbon dioxide's really very much small deviations here, negligible. When it comes to water, take a look. So water is clearly going to be slower than air because, the light particles are traveling, they hit the water, and they have to slow down because now they're interacting with the water's medium. So that's going to be a value greater than 1, and so forth and so on. Which is the highest on here, you noticed? Yeah, diamond and cubic zirconium. What do you notice about both of those things? They both have a tendency to do what? Ladies, come on, what do diamonds do? They sparkle. Oh, come on. Guys might wear diamonds, but let me just ladies, I know think about rings and when you get an engagement ring, right? Don't you want a nice big diamond so it sparkles and stuff? Come on. So that's what these are. Okay?
Is it because they are super dense? Is that why?
No. I'm not going to go into why just yet because it's in the next section, but just to allude to the fact that there's a phenomena that occur in diamonds and in cubic zirconia which cause them to sparkle, and it has to do with the N value. Okay, but I'm going to leave it just for now because we don't have enough time with the C day today to go into that yet. But we're going to discuss this. Okay, we're going to discuss how it works with the diamond and everything, and we're going to see that. God bless you. We're going to see that in a few examples. Okay, but there's a phenomena that occurs when N gets to be a certain value greater or a certain value high enough that this phenomena occurs, and you see some sort of a sparkle. Okay, we'll talk about that. But I want you to notice that all these values are all just greater than 1. Okay, greater than 1. Here's some liquids, here's some solids, and some gases. This table will either be given to you, or I'll give you the value of N, or I'll give you at least the speed of the light in that media, and you can divide it into 3 times 10 to the 8 to get the N value. But you'll be given enough information, you don't have to memorize these values. You should memorize that air is 1. Absolutely should memorize that. Air, the N value is 1. Now, Snell's law. Let's take a look at Snell's law. Snell's law tells us that the index of refraction of the first medium times the sine of that angle is equal to the index of refraction of the second medium times the sine of the new angle. The new angle. Okay, so theta I, again, is the angle the ray comes in at. Theta R is the refraction angle. Ni is the N value of the first medium, and R is the N value of the index of refraction of the second medium.
I was going to say, why don't you just use initial and final medium?
You could use that if you want, it's fine. R just means refracted. I means incident. I is not initial here. I really means incident. Okay? Angle of incidence. So, what I want you to think about is this. The higher the N value for a certain medium, like diamond or like another thing, the more it's going to bend. The more it's going to bend. The higher the N value, the more the actual light ray is going to bend. So what you'll notice is, let me give an example of this before we get into the math. If you have air here, let's say this is glass, and let's say this is water. Okay? Now imagine you have light rays coming into here that are parallel. So this light ray comes in at a certain angle, and another light ray is coming in parallel to that one, or another angle there. Okay? If we look at our table, the N value of water is 1.333. The N value of glass is around 1.5. It depends on which type of glass. Okay, which type of glass. So, if the N value is higher, it means that the wave is slowing down more. The wave is slowing down more. So it's going to bend more. It's going to bend more. So for air to glass, it's going to get pretty close to this normal here. For air to water, it's going to get close, but not as close. So if I were to call this theta I, right, these theta I's are the same. This would be like theta R1. and this would be like theta r2. This is just conceptual right now. This value here is going to be a greater angle, or this one changed more than the first one. So if the n value is greater, it means it's slowing down the wave even more. So this wave is bending really close to the normal. This one is only bending a little bit closer to the normal. So a higher n value means that the wave moves closer to the normal than any other media or another comparable media. Okay? Let's look mathematically at an example so we can see what this means. But again, higher n value, it bends closer to the normal. So example 1 says a light wave traveling through air strikes a flat, smooth surface made of fused quartz at an angle of 25 degrees to the normal. Determine the angle of refraction. So it's traveling through air at 25 degrees to the normal. So here's an angle of maybe 25 here. Here's air. Here's fused quartz. And our goal is to figure out what the angle of refraction is going to be. And if we're going from air to quartz, or air to some other material, what's going to happen in general?
It's gonna get closer to the normal.
Yeah, it's going to get closer to the normal. We don't know what the number is yet, but it will definitely be closer. So I'm going to draw something like this, just to emphasize that. And that's a bit of an exaggeration, possibly. We'll see what the angle is, and then we'll try and draw it to scale. But it's going to be something smaller than 25 degrees. Because again, going from air to another material, the wave fronts are slowing down. It's causing the wave to go from an angle like this to get slower and back up a little bit, and then go closer to the normal. So instead of following the path it wants to follow, which is this, right? Look, if I followed this path, let me follow it in blue. That's what it would really look like. Complete that black ray that comes in here, right? With this blue line. That's what it would normally look like. But we notice that the wave fronts are going to move closer to the normal there. Okay, so this here is my theta r in that little spot right there between the normal and the red line. So our goal is to figure out what theta r is. Okay, to figure out what theta r is. So let's use Snell's law. Okay, Snell's law tells us Ni sine theta I equals Nr sine theta r. What are my values here? Can somebody tell me what I'm going to plug in for what? And what are we solving for? What's one piece of info that you know? Tristan?
Sine 25 for
So theta I is 25, good. What else do you know? Look at the table on the last page if you need to. Okay, that is true, absolutely. But numerically, what do you know? Is 1. Incident.
Oh.
Ni stands for incident. Which of the incident side is air? You gave me the other one, right?
Yeah, it is one.
Okay, and then Nr is?
NR is 1.458.
And where did you get that from again?
This table.
Yeah, fused quartz is on the table on the previous page. The quartz is the refracted angle. Air is the incident angle, so air is going to be 1. Ni is going to be 1. Wait a minute, because I want you to see this next part. Now, we want to solve for what angle in the equation? Theta I or theta r? Theta r, the refracted angle, right? So divide by Nr. And you really need to follow me on this, because some students get confused. And we're not solving for sine of theta r, we're solving for theta r itself. How do you get rid of sine? You've done this now in Algebra 2. How do you get rid of a sine in front of something? Yeah, or sine inverse, right? Sine to the -1. So here's what you do now. This is going to be a little bit weird, but here's what you do. You write sine to the -1 of the whole thing on both sides. But sine to the -1 and sine, they in essence cancel each other out, even though they don't really cancel. They're inverse functions. So that's what theta r is. It's the sine -1 of this entire thing. So I recommend that you do the product and the quotient first in the inside, and then take the sine inverse of that answer. So go ahead and plug in. It's going to be 1 times sine of, make sure you're in degree mode. use your graphing calculator, not your iPad. 1 times sine of 25 over 1.458, you'll get a number, and then press second sine, bring up sine inverse of that answer. And you get an angle in degrees. Please check that right now.
Mr. Al, I have 14.1.
14.2?
14.1.
14.2.
Today?
Yeah. Thank you.
We answered 14.2.
Tristan, you gave me something that says 14.1 on it.
Oh, yeah, and it's the one that was due today. I don't know
It's not 14.1, right?
Yeah, I don't know what it's called.
That's what you want to do, right?
Yeah, 41 was due today.
Oh, right.
14.1 was due on the day of the test.
Did you collect 14.2 already?
Yeah, in the beginning I said any hard copies.
Oh, yeah.
Hey, check with the person around you to make sure you got the right answer here, please. Alright, so this is sine 25 here, right? That's right. The one is there, that's good. Now this is just sine negative 1. So if you're reading what that means is you do inside first, and then you go to the calculator and press second sine. So you had it right now. Can I push it? Where is your numerator? One plus sine 25. Alright, now you're going to press the second sine, the second base. Take the sine and that change. And it has to be less than 25, right? And it is less than 25. Anybody having trouble calculating this? What do we get for a number?
16.85.
Yeah, good. 16 and change. 16.9, I think it was. Okay. How do we know that this is generally correct?
Oh, because it's less than 25.
Yeah. We said that when you go from a fast-moving medium to a slow-moving medium, the light ray is going to bend toward the normal. So if we started at 25 degrees, it's got to be something less than 25 degrees, right? And 16.9 is indeed less than 25 degrees. Let's do the last one now.
No.
Can you?
Yeah, you just wait. I need you to see this today. We have a short period. It's not a normal day. This one's a little bit different, that's why. A light wave travels from air to an unknown medium. Unknown. If the angle it hits the medium with respect to the normal is 30, angle of refraction is 12, determine the material that it passes through. Well, you're not going to know the material, but you can find the n value of the material, right? And then look at the table. So let's go ahead and do that. Yeah. We know theta I is 30 degrees. We know ni, because it's in air, is 1. We know theta r is 12 degrees. We're trying to find nr. So we know the angle which light hits it with. We know air is 1. We know the angle of refraction is 12. Find out the material that causes this angle of refraction. So find out nr. So write your equation out, just solve for nr. This is much easier than the last one. But then we have to look at our table to figure out which one it actually is. So here's our formula. Divide by the quantity sine theta r. Everybody see that, please? You're not dividing by sine and then dividing by theta r. It's the quantity sine theta r that you're dividing by. So I would do 1 times the sine of 30 divided by the sine of 12.
Why didn't we do that in the last problem?
Because the last problem we were looking for the angle, weren't we?
Oh, yeah.
Now we're looking for the nr value. If we find nr, we can find the material. What do you get for nr in this problem? When plugging in. 2.4. Go to your table. What is closest to 2.4? Diamond is, okay? So this material that causes an angle of 30 degrees to suddenly alter itself so much that you're at a 12-degree angle, okay, and you're at a 12-degree angle, this material is diamond. All right? Yeah.
Is there no units for like R
That's a good thing or N, right?
and the other thing?
N. That's another point I was going to make and I didn't say it earlier. What was the formula for N? N equals C over V, right? Remember earlier? N equals C over V? They're both meters per second, so what happens? So there's no units. N is dimensionless, like mu. Like mu, remember, has no dimensions. Mu is FF over FN, while N is C over V, both meters per second over meters per second. So there's no units for the N values. Julian.
At the on the table, like the refraction for various substances. Why is it? What's the significance of keeping them at 20 degrees Celsius? Is that just like a constant?
Well, temperature changes materials, makes them with thermal expansion. So if it's at a higher temperature, the molecules are going to expand more. Okay?
Why 20 degrees Celsius?
It's just the standard temperature and pressure.
The gases are done at 0 degrees though. The rest are done at 20. Liquids and solids are 20, gases are 0.
Why are they 20 versus 0? Why they're not all at 0? Why they're not all
Why
at
not
20?
all 0?
Or why are they all at like 6?
Oh wait, if they were at 0, then water would be ice.
0 is the freezing point. Water would be ice, so liquids wouldn't work, so it wouldn't work for water. So I'm guessing that's why that's at 20. Solids, it doesn't really matter, but what is 20 degrees in Celsius in Fahrenheit? 0 Celsius is 32 degrees Fahrenheit. 20 Celsius, multiply it by 9/5. That's going to be 180 over 5. It's going to be 20, 16, 36, 32, 78. It's room temperature. That's what it is. 20 degrees Celsius is room temperature.
78 degrees room temperature.
Yeah. Or 76, or it's a number like that around there.
Really hot. Wow, 78 degrees.
So the 20 degrees room temperature is 0. I'm not sure why the gases are at 0 though, because those could be at higher temperatures. Right? Usually standard temperature and pressure units are used. The homework on this, guys, okay, there's homework on. You're going to see 3 problems on there. These are in tomorrow. These are in tomorrow.
You think we're gonna have school